All right. We have another question that we are going to check. Remember our steam plant, just like what we had in our N5, but only that we just have some other things that are considered on our steam plant flow diagram, where we now consider the part of having the preheater, that is the air preheater, the use of the fuel, which is something that we were not having in our N5. So there are just one or two things that you just need to add, but the basics of our N5 is still there about the steam generation. All right, so we're not going to waste much time. This is November 2022 exam, question 4.1, where we are given to state the first law of thermodynamics in words, and that is 3 marks for that. The first law. There are so many laws, 3 laws, but they need us to give the first. All right. So the first law, as it states that in a thermodynamic cycle, the sum of the net heat supplied into the system, and the systems actually, and the network input is 0. So let me just write it somewhere here. So we are simply saying that is in a thermodynamic. Okay, so that is in a thermodynamic. So you're gonna have something of this nature, thermodynamic cycle. The sum of the net. So this is the sum of the net heat supplied. All right, the net heat supplied into the system, into the systems. All right, and the network. So it is affecting the whole network there. So and the whole network input is 0. So that must be equal to 0. So that is the most important part, that everything that you are considering, the sum of everything must be equated to 0. All right, so these ones, guys, we can write them in our own ways as long it is part of that. My major part is this question, 4.2. 4.2. All right. We are given here this whole information, this and that. A steam plant operating at a pressure of, so it's a steam plant. All right. This is the operating pressure, the pressure that is at the superheater. And it also, I said this pressure, it affects 2 things. The output of the superheater and its input, which is the output of what? Of the boiler, because you'll be having a boiler here. So that pressure, it affects at the boiler, at its output, and it also affecting at the output. So it is the input and output of the superheater. That is what we are simply saying. That pressure, it does not change. I talked about this in our N5, about this pressure, this one. And also the temperature, this is the temperature of the superheated steam. Remember, it produces what? Superheated steam. Okay? So that means in this case, we've got the pressure and this, that, and also they gave us the specific heat capacity of the superheated steam. If you are not given that, it means the information that you have here, you will use it on the superheated table. Remember, we have got the information that is affecting only the steam. Then we have got the part of the superheated steam on from our steam table, where you'll be having pressure, and you'll be having the temperatures there. On that condition, that is where you will find your H soup. You take the pressure and its temperature. But the moment they give you this specific heat capacity of the superheated steam, it means they are expecting you to find your H soup, which is the superheated steam, from the formula of what? Of Hg plus, remember our formula, it states that we're going to have Hg into Cp, that is T soap minus Ts. Okay, yeah, that's our formula there. So you're going to have this formula. Remember these formulas, I talked about them in our N5. No problem. So they gave us a lot of information, but I want us to have it in form of a diagram. So let us check what we are given. If we check there, they're talking about at the entrance of the superheater, the steam is, it has got this wetness, meaning to say that is from the boiler. The boiler, remember, from the boiler, the steam can be dry or it can be wet. So this part here is from what? The boiler. So it means we've got a what? A boiler. Then also they talked about something here. All right. There's something that I needed us to take note here about the economizer. The economizer increases feed water temperature from. So there is also an economizer. So we've got an economizer, a boiler, and a superheater. So that means we are going to have our diagram in this nature. Let me just have a sketch because there are three things that we have. So remember in our N5, I said, so this is just like the flow diagram. We're just going to put it this way. So you're going to have our economizer, then to the boiler, to the what? To the superheater. It is very, very important that you do a sketch because sometimes they do give you this, maybe it's just a boiler and what? And a superheat. Then you'll be wondering, why am I using, sometimes I use 3, on the same formula, I'm using 2. Then you'll be saying, why is it that these numbers are changing? It's because of this diagram. You must at least know that this is the input. So you've got the 0.1, the 0.2, the 0.3, and 0.4. Remember, we said we've got what? The economizer. Then we've got our boiler here, which is our evaporator. Then we've got what? The superheater here that we have, where we're going to have the superheated steam. So if we check the first information, this one was about the superheated steam, the pressure of 3.5 and the superheated steam temperature and the specific heat capacity. So let us just indicate that next to our diagram, the pressure of 3.5 megapascal. Remember 3.5 megapascal, I said you multiply by 1,000. So it will be 35,000. All right. So this pressure, that means 3,500, and so that will be 3,500 at the output of the what? The superheater. This is at the out. We are producing this at. So this is at 3,500 kilopascal. Remember, it was 3.5 megapascal. You multiply by 1,000 to convert to kilopascal. But like I said, also, this pressure is the same as the pressure at the 0.3. So take note, it is the input and also the output to the boiler. I mean to the superheater. So as for the boiler, it is the output that is at the boiler here. All right. But it is the input of the superheater and also the output. That is the pressure that you're given. Then the temperature is it produces. This is the temperature and the output of the superheated and the specific heat capacity. So these two we are given, guys. That is T sup. In this case here is given as 305. All right, so this is 305 degrees Celsius, and also the specific heat capacity of the superheated steam, because sometimes it can be a gas. Do not confuse the two. The superheated steam for the superheated steam and the superheated gas are two different things. I shall talk about that if we have a question that talks about that, because I see a lot of you guys have a challenge on taking these two. So that's why I spend much time taking this information. Then they are saying the plant burns fuel with a calorific value of. So we're given the calorific value. Remember, this is for the fuel. So this one does not even need us to indicate on the diagram. We can just write it aside here. So we have got a calorific value of 32 megajoules. So 32 mega to kilo, like what we did to kilopascal. We multiply by what? By 1,000. So that will be 32,000 kilojoules per what? Per kilogram. So there we've got that is right. It's like now I'm writing that CV, like, okay, it's like this calorific value. Let me just write this. Okay, I hope it's clear. That's your heat value. All right. What else? Then they are talking about the economizer there. The economizer increases. It means you increase from a certain to a certain. What is it being increased? The feed water temperature. From this temperature to this temperature. This is happening on the economizer. It is the feed water. So meaning to say the part of the economizer here, we are talking about what? It is the water that we have here. Here we're talking about water. Take note, the feed water, there we still have water as it is, and we are given its temperature at the input of the economizer. It increased from this temperature of 24.1 degrees Celsius to a temperature of, that means it's going to be T2 at the point 2. Like I said, according to our diagram, this is 1, 2, 3. So this is 83.7 degrees Celsius. Let me finish about this one before we have a confusion, because some of us here, I don't know what happens. This is it, guys. Remember, this is water that we have. And yes, it's going to enter the boiler now, where we are told there, I think when we read, we are told that it is this one wet. We're given the percentage of the wetness. It means this steam is wet, but it can be dry. When they tell you that it's dry, it means here you are going to take this as your Hg. At this point, remember, we need the enthalpies. From this point 1, we need H1, we need H2, we need H3, we need H4. At this point 1, point 2, point 3, point 4. So what is going to represent H1? H1, this is water that is entering. So the enthalpy for water is our HF. You know that, guys. All right? That is for water, HF. All right? When it is dry, which means H3 is going to be equal to Hg. But this one is not dry. So it means H3 is equal to what? To H wet. You must know this. I talked about this from our N5. So this part, they are assuming that you know all this part, because that was our N5, this one, if you take note. So where do we find HF? At this temperature, like I said before, at 24.1, let us go and find HF. Let us just finish this part of H1 and H2 because they are direct. All right. So under the word, our saturation temperature, all right, we need to find HF there, which is the enthalpy of what? Of the water. So let us see at, remember we said our temperature is what? 24.1. So at a temperature of 24.1, do we have that S? Here it is. Here it is. All right. So this is where we are. 24.1. I saw it somewhere here. 24.1. This one under the temperature here. So we are going straight under this. All right. So as we need what? HF, not these other values. So it's just going to take our HF, which is 101 kilojoules per what? Per kg. This is HF kilojoules per kilogram. So that is 101. Okay, let us write it down. So we have HF there, which is representing H1. So this is 101 kilojoules per kilogram. All right, we do the same thing for H2 because this is still underwater. It is still water that we have. So it means our H2 is also equal to HF, but at this temperature of 83, the temperature was just increased, but it is still water. So it's gonna be HF again at this at this temperature now that is being increased. So we're gonna check what is the temperature. Remember our temperature 83.7. We're still under the what? HF. Remember this is the column for HF. Just gonna go down straight under HF at 83. 83, that's somewhere here down. This is somewhere here, guys. 83.7. So we're going to take this column of 83.7. Remember, this is the part that is under HF, this one. HF is under this. So guys, I just hope you see. All right, so that means the value that you're going to take under this TS, which is our temperature, the value of HF is corresponding there is what? 351. So that is our HF. If we check here on top, it is corresponding to HF. So we have the corresponding value there at that temperature, 351. So that's 351 kilojoules per kilogram. So here we've got a 351 kilojoules per what? Per kilogram. So you're gonna do the same thing, understanding what is happening here. Is it wet or is it dry? And so forth. But these ones, I just want you to feel, because this is still water. You can just take direct from your steam table. All right, so let us move on. While absorbing 2000 100 kilograms supplied energy. So what is it that we have there? They are saying the economizer, it increases the feed water and it is absorbing this, and the economizer is absorbing this energy, 2,100, the economizer. So that means we are given the energy taken in the economizer, which is given as 2,100 kilojoules per watt per kilogram of the supplied energy. Remember, how do you calculate these energies? I talked about this, that the energy from economizer is going to be mass of steam over mass of fuel into H2 minus H1. If it is for the boiler, H3 minus H2, superheater, H4 minus H3. We talked about that. All right. So they gave us that. So meaning to say, somehow you can play with that formula to find something that is missing there. They won't just give you this value because you are the one who is supposed to calculate it. So you must have that question in your mind. Why are they giving you this? Something has to be calculated there. No problem. Let us see. At the entrance to the superheater, take note, at the entrance to the superheater, steam has a wetness of 2.13% at the entrance of the superheater here. This is where our superheater is. At its entrance, that means it is the output of what? Of the boiler. So they are saying the output of the boiler. In other words, that is what they were supposed to say. All right? They are saying at the output of the boiler, which is the entrance of the superheater, when it is entering here, that is the output of the boiler. The steam is what? We are given the percentage of the wetness, that it is 2.13% wet. We never talked about being wet of a fraction. We talk about being dry, the dryness fraction. That is the one that we know from our calculation. So we need the dryness fraction, which is x. So from the wetness fraction, x is going to be 100% minus 2.13%, which is going to give us something like 97.87%. So that means here at the output of the boiler, which is the entrance of the superheater, x representing our dryness fraction is going to be 0.9787 as a decimal. Like I said, guys, it is very, very important that you know the condition of the boiler, what is happening after the boiler, because they can say that the steam that we are having there it's dry. We are having dry. It means H3 is no longer equal to H wet, because here H3 is equal to H because we are given what? It is wet. We've got the dryness fraction. So H3 is equal to H wet. And we know that H wet is equal to what? H wet is equal to HF plus X HFG. This is what we know from our N5. So sometimes they might say it is dry. If they indicate that it is dry, H3 will be equal to HG. There it is dry. So HG, where do you take it? Don't calculate HG. You take it at this pressure. You just go straight to your steam table. You take your HG. But on this one, we have to calculate H wet. All right, let's just finish up and see. So HF, we know this. H wet is equal to HF plus X HFG at the given pressure. So this HF and HFG, they operate at the given pressure, at the pressure of what? Of 3,500 kilopascal. So all these calculations, if you are doing them, don't erase them. They are part of your working, which is supposed to be seen. Whatever that you're doing, maybe you're going to use 2 booklets or 3 booklets, I don't know. But the working has to be there. Don't erase it. So it means our H wet at 3,500 kilopascal is going to be what? HF. All right, let us go to them. That. So in the next classes, guys, I won't be showing you this steam table, and I hope now you are getting used to this. Okay, 3,500 is this one. So let us go to 3,000. Sorry, this is 3,500. 3,500 here. Straight. All right, like that. So what do we need there? Remember, we said we need HF at this and also HFG. These are the 2 that we want. So HF there is 1,050. All right, that is 1050 there. And we've got HFG, which is 1752. So it is very, very important that you have this. All right. So 1050. Let us go back and substitute. Take note, it's HF and what? HFG. All right. I hope you understand me, guys. We're not even supposed to calculate this, but I'm saying we can do that. All right. Because those points definitely are going to need them. So HF at 3,500, we saw that it's 1050. So that means we've got 1050 plus X, which is our dryness fraction of 0.9787 times HFG. We saw that it was 1752. So we combine this, we are going to obtain 2764,982 like that. This is kilojoules per kilogram. Like I said, do not throw away this information. It is supposed to be shown some way. You have to calculate these values, which is fine, but we are supposed to have this. Remember, we said H3 is equal to H wet. And we found this, our H wet as what? 2764,982. This is kilojoules per watt per kilogram. This is just the output of what? Of the boiler. That's how we fill in our information. All right, so guys, we have this. Like I said, we're not even supposed to calculate it now because we'll need it later on our calculations. But let us see. Now they are saying here, this is another part that is important about the preheater. The preheater heats the air from this temperature to this temperature. What is heating? The preheater. We are talking about the preheater there. So remember, the preheater, it is the part that we are having the air that is being affected. It's an air preheater. It has the temperature, the input and the output. Temperature for air at input and the temperature for air at the output, which is being affected. This preheater is affected by what? By the fuel. All right. Remember from our flow diagram. So meaning to say, let us just have the condition of a preheater here. So about the air preheater, they are saying for the air preheater, we are given the input temperature Tn, the air entering at 25 degrees Celsius as we are given, and T out at the output, which is 119 degrees Celsius. We shall talk about this. Then the air fuel ratio is 18:1. Air fuel, remember, whenever you're talking about the air fuel, it can be mass of air as to mass of fuel. So this is our air fuel ratio. Remember the air preheater, like I said, is affected by the fuel. So that is why they are giving you the air fuel heater, the air fuel ratio there. While the temperature at the chimney base is, at the chimney base, we've got a temperature of, this is the best temperature, the temperature affecting the chimney, which is where we are being affected by the what? The flue gases. The chimney is the one that is affected by the what? By the flue gases. All right. So you have to be able to understand this. So the part of the chimney is the part of what? Of the flue gases. This is the part of the air. All right. So at the chimney there, we are given the temperature that is affecting our chimney, which is 117. The best temperature is the output temperature, this one. This is your output temperature. All right. So also we are given the specific heat capacity of air. Take note, the specific heat capacity of air. Like I was saying, there are two things that you're not supposed to have a confusion when you are given. Here we are given the specific heat capacity also on top here. But this one is for what? For the superheated steam. So sometimes they will give you a specific, the specific heat capacity of air. and you are not given this one, never use this to answer this one. No. Once they do not give you the specific heat capacity of the superheated steam, expect that they will give you a pressure and a temperature that is enough for you to use on the superheated steam table to find your H soup. On that condition, it shall be like that. But once they give you the specific heat capacity of the superheated, these temperatures, if you try to go with this temperature and this pressure, you won't find these values from your superheated steam table. So they won't do something like that. They know what they are doing there. So do not confuse these two. This one is the specific heat capacity of air, for air. All right? It's now dry air. So it's just going to put a G there to represent that it's a dry air. So we've got the specific heat capacity for the gases in this case, which is 1, sorry, we are given the first one. I'm taking two things at the same time. So the first one was for air. So first one is for air. So we've got CP, air in this case, which is 1,005 kilojoules per kg Kelvin. Then the other one that we are given here is for the flue gases. This heat capacity again, but this one is for flue gases. All right, the second one. So the first one is for air, then the second one, this one respectively. So the one that is following is for the flue gases. So it is the specific heat capacity. Definitely, guys, they are dry. So this is CP for the dry gases in this case, which is 1,07 kilojoules per watt per kg Kelvin. So this is what we are given. This is what we have. So now the question is that from this information that we have, remember I said the chimney best temperature is our T out. So what is going to be T in? T in is the temperature that is at the preheater. The preheater temperature, remember it will be like this. The air preheater is somewhere here. This is your air preheater. Then the chimney, it is now like this. This is the part of the chimney. So the best temperature, which is the inlet of air, is the one that is also the best. I mean, the temperature at the inlet of the chimney. Then the best temperature of it is T out. Whilst this our air preheater here, it has got its output, which is TA2 here at the output. But this being taken from what? Remember, it is being taken from what? From the fuel. That is why we are also talking about the part of the fuel being involved there. All right. So the question is that, so the ideas that I'm simply saying is that our T in this case is the same T in that we had here, which is 25 degrees Celsius. So do not confuse. But this is the part of what? Of the chimney, this one. And this is the part of what? Of the air preheater. All right. Let us see our questions. That is, so it's better for you to take much time taking this information. Then when you're answering, it's just, we are just flowing here. So the first question was to use the steam tables to calculate the following, this and that, our final answers to 2 decimal places. All right, so guys, this instruction, I did not even follow that one to say the answers are needed to 2 decimal places. On my preparation, I did not see that. I used 3 decimal places. So you are going to use 2 decimal places, but already, guys, I did this preparation. I did 3 decimal places. I'm seeing that. So they are saying, calculate this to 2 decimal places, all right? But like I said, guys, as for me, I used what? 3 decimal places. So the mass of steam generated in kilogram per kilogram of fuel burnt. Whenever they're asking you this type of a question, they need the mass of steam over the mass of fuel per fuel. That is the mass of fuel. That is what they're asking you here. So where and how can we find MS over MF? All right, this one, we're not going to use it for now. We are on this information that we have at on this part. Where and how can we determine this value? All right, so this is 4.21. All right, 4.21. So we need the value of mass of steam over the mass of fuel. That is for us to obtain per kilogram of the fuel burnt. But like I said, they are not going to just give you this for nothing. You see now, they are not just going to give you this for nothing. Why did they give us the energy, the heat value that we obtained from the economizer? It is because that formula, it consists of MS over MF. Remember, I talked about that formula, and I said the Q economizer is given as the mass of steam into what? We're gonna, okay, let us first have this mass of steam over the mass of fuel, then into the difference. This is where your economizer is. So the enthalpies that you affect is the output minus the input. So the output of the economizer is H2. So that will be H2 minus H1. If it was Q for the evaporator, we're going to use mass of steam over mass of fuel, Q3 minus QT. Maybe they give you the one for the superheater, you're going to use H4 minus H3. All right, so here's H3 minus H2 for the boiler. It depends with what you are given, which energy, which heat are you given, the heat value that you, the heat energy that you're given there. Is it for the boiler? If it was for the boiler, you're going to use 0.3 minus 0.2. It is because we have the economizer, and according to our diagram, the economizer is affected by 0.2 and 1. So that's it, guys. This is what we want. So how can we find this? We simply have to divide by what? H2 minus H1. H2 minus H1. So this will cancel. So we've got the mass of steam over the mass of fuel, which is this part that we want here. Okay, so let's leave it aside. I hope you understand me, guys. So the mass of steam over the mass of fuel, according to our calculation, it is going to be given as Q from the economizer, all right, over H2 minus H1. So that's the mass of steam over the mass of fuel is the Q from the economizer, which we are given there. That was 2,100, right, from the economizer. Our Q is what? 2,100 kilojoules per kilogram. Then over H2 minus H1. Now you don't need the steam table because already we found these values. So that is the advantage now of finding this straight. We just take our values. What is our H2? We calculated this. We stated this before. 351 minus H1. What is our H1? 101. I hope you still understand. If not, then you can just pull back the video so that you can cross-check how did we find these values. All right, so this was going to give you 8,4. So that was going to give you 8,4. This is kilograms per kilogram fuel. Remember, this is taken per kilogram of what? The fuel. So that's the mass of steam over mass of fuel. So this one, definitely we are going to need this in our calculation. So MS over MF is equal to 8,4 kilograms. This is mass, kilograms per kilogram fuel. All right, this one we are going to need it. All right, I'm just reserving this for calculations, guys. That's why I'm erasing this so that I do not go far from the diagram, so that you understand me if I'm working closer to the diagram. All right, so that was the first question. We are done. We have the mass of steam over the mass of fuel there, the mass of steam generated per kilogram of the fuel burnt. All right, so let's move on to another part. 4.2, the thermal efficiency of the whole plant. All right, there it's important. The thermal efficiency of the whole plant. Of the whole plant. Okay, I talked about this formula for the thermal efficiency and said that in order for you to have the thermal efficiency, this is our formula here. So this is 4.22. 4.22. In order for us to have the thermal efficiency, we understand that this is given also the formula, we have it. But you need to understand your formula. I say this is MS into, on the enthalpies there, they will give you from the formula sheet you'll be given as H2 minus H1. It's a temptation that you're given there. Take it this way. This is going to be H, the last part minus H of the first, enthalpy of the first. All right, I'm going to explain this over the mass of fuel times the calorific value. Remember, the calorific value is supposed to be in kilojoules per kilogram. I explained that before. But yes, my point here, when they need you to calculate the thermal efficiency, remember, this is for the whole or for the entire plant. So for the entire plant, it means we are considering the the last one at the end of the plant. The H first is the one at the beginning of the plant. That is for the whole plant. Guys, you must understand this. So it means on our formula here, this is supposed to be H for according. That is where I'm answering those questions that you ask. Why do we use H3 or H2 or H1? The last one from our diagram is H4. So that formula that you have from your formula sheet is a tempting formula. H first, the first one is H1. So if our diagram was maybe there were just 2 points, maybe there's a boiler and a superheater. This will be 1, this will be 2, this will be 3. This is the boiler and this is a superheater. So our H last is H3. Our H first is H1. So it's going to be H3 minus H1. It's no longer H4 minus H1. This diagram, that's why I said you must have this sketch. It helps you to know your points. That is where that information now plays a role. If you just take it, your information, you just answer 1, 1, 1, 1, you get confusion at the end. So it means we need H4. We need H1. But H1, if we take already, we stated this. H4, we never talked about this, but I just mentioned in passing about this H4. That is because we are given the specific heat capacity of the superheated steam. They expect you to calculate the H sup there. The H4 is equivalent to the superheated, that is H4 is equivalent to H sup. But the moment you are given the specific heat capacity of the superheated steam, then they're expecting you to calculate it from Hg plus Cp for the superheated, because we are given it into T sup minus Ts. That is what they are expecting from you. That is the idea. They expect you to have this. All right. So where are we going to have this? From which points? Okay. We know that the Hg and the Ts, these are the ones that you just need. They are found at the given pressure. So this is at the pressure of what? 3,500 kilopascal. We have the Cp already given, the T sup already given. These are the only 2 things that we need. So you find them at the given pressure. So that means H4, which represents H sup, is going to be Hg at, okay, let's go to that temp. Remember, to that pressure, we talked about this pressure before. I talked about this pressure here. At 3,500, this time we need Hg and Ts. So this is our Ts, the saturation temperature, which is 242.5 degrees Celsius. All right. And what about Hg? This is our Hg here. At this pressure, our Hg is 2,802 kilojoules per watt per kilogram. So these are the 2 things that we need: Hg, this one, and Ts. Our Ts there. So Hg, we got this as 2,802. Remember, guys, the value that we got there. The Ts, this one, it is 242. Remember, this is we got at 242.5 degrees Celsius, 5. All right. So let's substitute the Cp for the superheated steam is 3,1125 into T sup. The superheated temperature there was 305 minus Ts, the one for the saturation, which is for water 242.5 degrees Celsius. So we have to subtract this. So that is our H4, which is our H sup. Okay, and this was going to give us 29 296,53 something like that. So it's gonna be 531 to 3 decimal places, 531 kilojoules per watt per kilogram. Like I said, guys, I used my values to 3 decimal places already. So we have H4 here. That is 2996,531. All right, there we are. We are done. So this H4 represents our H soup. So the question is not that H4, but the question is, or it was on the thermal efficiency. But the thermal efficiency is limited, well, we're limited to determine it because of what? We do not have H4, which is our last enthalpy. Now that we have calculated this, we can find our thermal efficiency. Remember, as a percentage, you multiply by what? By 100%. So that is it, guys. This one we calculated it. The mass of steam over mass of fuel, we have this value. This is the one that we obtained here. Mass of steam over mass of fuel. Remember, we have it. Mass of steam over mass is 8,4. So meaning to say, when you're substituting, you're just substituting this as 8,4. All right, so this we got 8,4 multiplied to, already we have taken this. So you're going to be left with what? H last minus H first, which is our H4 minus H1. So our H4, we calculated this. We got 2996,531 minus H first, which is our H1. Already H1 we have. That was 101. All right, everything over the calorific value in kilojoules per kilogram. All right, remember these units are kilojoules, everything, kilojoules per kilograms, everything, kilojoules per kilogram. So also this must be in kilojoules per kilogram. So that gave us 32,000. Remember, I talked about this. As a percentage, we multiply by 100%. So that was going to give us the thermal efficiency, which is 76,007688 and so on. So it's going to be 007688 and so on. So to 2 decimal places, as per the instruction of our question paper, is going to be 0.1%. All right, but as for me, I've got something like 76,008 if you're using the 3 decimal place concept. All right, but that was it, guys. So this is it. That's your thermal efficiency. We have our thermal efficiency. All right, so you do not know, maybe we might need this thermal efficiency later on. Let us just write it aside. So we got 76,01%. So this is the one that you got, guys, for this one, because I'm rounding off to 2 decimal place. But as for me, like I said, 76,008 is the one that I got. I'm just saying, if maybe we are going to need this, I'm going to use it like that, because it will affect my calculations, guys. It will affect the whole of my preparation. So as for you guys, you just have to round off to 2 decimal places as per instruction, so that you do not also miss the instruction that you're given there. All right, so that was it there. We have got our thermal efficiency 4 marks. Then let's see another part. They are saying, here we have to be clear here. There we have to be very, very clear. There are so many things that we need here. They are saying 4.23, the heat energy absorbed by, just like what we were given before here. Remember, they told us about the economizer, that it is absorbing this energy. So they want us now to find the heat energy absorbed by the evaporator, the superheater, and the air preheater. And the air preheater. And the air preheater. So there are the 3 things there to be considered. Okay. Let me put it down here again. I'm going to use this space here. All right. Remember, what do they need here? This is 4.23. Guys, I'm not even rushing. No, don't make me rush, so that you understand me. If you understand one question, then you can do as many questions. That's the advantage. All right. So this is what they're saying. We are supposed to find the energy absorbed in the evaporator. That's the boiler there. So we've got the evaporator, the energy absorbed in the superheater. All right. And also for the preheater, our air preheater. These are the three. All right. Let's talk about the evaporator. Remember, I had this and I talked about that one of the economizer. How did we find this? What was the concept? Remember, we're saying the mass of steam over the mass of fuel. But what affects here now is the output minus the input. To that, what is affected? Output minus input. So in this case, we're talking about the evaporator. The output of the evaporator is H3. The input to the evaporator is 2. So it's going to be H3 minus H2. You have to be careful on the formula there. Which points are affecting what? The evaporator at its output and at its input. So that means our Q evaporator, according to our diagram, this is 3, this is 2. So it's going to be mass of steam over the mass of fuel into H3 minus H2. That's the part of the evaporator, H3. All right, so mass of steam over mass of fuel, we calculated this, 8,4 kilogram per kilogram fuel. So we've got 8,4 times H3. Already we've got our H3. We calculated this. We got 2764,982. Remember, that was our H wet there. H2, we stated this before. So this is 351. We're just inserting our values. So that's it. Just like that. Just like that. So if you have already calculated this, it's not a struggle for at all. So that was going to be 202, 202. All right, it's actually 20,000 there because the 20,000, 277,4, 4. So it's gonna be 88 like that. So this will be 88, which is gonna be 9 to 3 decimal places. That's per kilogram of kilogram fuel. But according to your instruction, they are saying to 2 decimal places. So that means as for you guys, your answer is supposed to be 45. All right. It's going to be 45 there, according to you. But according to what I've done already, it was 449 to 3 decimal places. No problem. So this is for the evaporation. All right. Let's hope we remember this, guys, because I just need to remove this and calculate for the what? For the other one that follows, which is for the superheater. So Q sup, just like what we found there, the mass of steam over the mass of fuel. But what is affecting the superheater? The output is F4. The input to the superheater is 3. So it's going to be H4 minus H3. All right. So they've got H4 minus H3. All right. The mass of steam, mass of fuel, everything we have. This is 8,4 kilogram per fuel that we are given. So times H4, we calculated. This is our H soup, remember? That is 2996,531 minus H3, which is our H wet from the boiler. We calculated this. That's 2764,982. So that was going to give us the Q absorbed by the evaporator. So by the superheater. So the superheater was going to absorb 1,945, that was going to be 0116, something like that. So to 2 decimal places, it's just going to be 01. All right. So this will be 01 kilojoules per kilogram fuel. All right. So that was it. But according to me, it was going to be 0.012 to 3 decimal places. No problem. No problem. Okay, so that was it there. That's your heat. That is absorbed by the superheater. All right, the last one that we have is for the air preheater. So the air preheater, what is affecting the air preheater? That is the question. We are talking about air, so we need heat from the air. This was the heat from the water, steam, water. We are talking about the enthalpy of water, but there we are not having H enthalpy for. We don't have enthalpy for steam, guys. I mean for air. No, we do not have that. So how do we calculate the Q that affects air? Because it's the preheater, which is the air. So it is Q air is going to be the mass of air times the specific heat capacity of air in this case times the change in temperature. Remember, at the preheater, I said there's T in for air and there's T out for air. That's it then. We use the specific heat capacity for air with the mass of air and the change in temperature for air. There's no longer enthalpies there. There's no longer H this for air, guys. It does not exist. So you ask yourself that, where and do I have this value? Am I having this value? The mass of air, are we having it? No, we do not have. But we are given, remember, the air-fuel ratio. That is where it plays a role. Air-fuel ratio is 18. Remember, guys, this is the super, I talked about this. This is your air preheater, this one. Your air preheater. We have the T in, the T, but if we check the air fuel ratio, what does it mean? It means we can even write, because it's air as to fuel. So I can write it as the mass of air as to the mass of fuel per a kilogram of fuel. It means the mass of air is going to be what? Be 18. So it means the mass of air is 18 kilograms per kilogram fuel, per a kilogram fuel. Guys, I hope you understand me. We have from ratio. All right, so this is what we're going to take. With this, we do not need the mass of gases like that one where we have to play around with the ratio. We find the mass of gases there. No, we need that one as it is. Direct the mass of air is given. So that is 18 kilogram per kilo, because they need this per kilogram fuel, per. So the kilogram fuel is already at 1 kilogram. So the mass of air there is 18 times the specific heat capacity of the what? The air at the preheater. What is the CP there? That is 1. We are given there 1,005. That's where I say do not confuse with the one for water. This one is for air. 1,005 times the change in temperature. Definitely this will be T out minus T in, or T2 minus T1. So what is the input of the preheater? I mean the output of the preheater, 119. The input, 25. We subtract. So that's 119 minus 25. Guys, you must know this. All this information, you must know it. So that was going to give you 1,700,46 to 2 decimal places. That is kilojoules per kilogram fuel. Remember, this is taken per kilogram fuel. Per kilogram fuel. Per kilogram fuel. That is the idea there. That is the idea. So this is Q for air. Like I said, if we are given, because they can ask you the one for gases, if it was the Q for gases, which is, we are going to use the mass of the gases this time, mg times the specific heat capacity of the gases times the change in temperature for the gases, for the flue gases, where this mg is the one that you use again on the ratio, it is equal to mf plus, so the mass of fuel plus the mass of air. So let's just, according to the ratio, remember it starts with MA as 2. So let us just do that so that we do not have a confusion. So this will be the mass of the gases per kilogram. Remember, it's kilogram per kilogram what? Per kilogram fuel. They can ask that. Guys, you have to be very, very careful how you take our information. All right, so that's, they can do ask this one. So this one, it was for air. I think we can just erase this for the preheater, everything. So we have answered every part of our question there on this part of 4.32. Okay, let's check 4.32. Then another question, it is 4.24. This is 4.23, then 4.24. All right, on 4.24, they are saying we are supposed to determine the percentage heat carried away with the flue gases, the percentage heat carried away. So the percentage heat carried by what? By the flue gases. So the idea there is that if it is the percentage that is taken by the flue gases, a percentage, guys, it is supposed to be that part that we are talking about, which is the flue gases, is the heat, remember, is the heat for the flue gases, over what? It must be over the total energy. It must be over the total energy for us to obtain the percentage. It must be over the total percentage. I mean, the total energy. But what is going to represent now the total energy? What's going to represent that? It is from the calorific value as a person. The calorific value is our total energy. Q in, remember from your heat balance sheet, the Q in is the calorific value. So they simply need you to find Q for the dry gases, the flue gases, over the Q, which is our calorific value in this case, times 100%. That is what they're simply asking you to do. So where are we going to have this? Guys, this is the one, and I erased that formula, but I was talking about, this is the one that I was actually talking about, if you still remember, where I was saying this is the one for the flue gases, and the flue gases are ones affected from what? From the chimney. That is where we have our flue gases. That's where we have the specific heat capacity of the flue gases there. We have. So it means we can calculate that. The Q for the flue gases is going to be the mass of the flue gases, which is dry them, times the specific heat capacity of the flue gases times the change in temperature, which is the mass. Remember, that is mg that I was explaining, that the mass of the gas is taken from our air fuel ratio, this one. Remember, the mass of air is 18 kilograms per kilogram fuel. It means the mass of fuel is 1 kilogram. So the mass of the gases is going to be the mass of air plus the mass of fuel according to our ratio. This is 18 plus 1, which is going to be 19 kilograms per what? Per kilogram fuel. So this is the mass of what? Of the gases. That's how you find it. So that is going to be 19 times the specific heat capacity of the what? The flue gases, which is our specific heat capacity there is what? You see, each and every has got its own specific heat capacity. Specific heat capacity for the air, specific heat capacity for the flue gases, the specific heat capacity for steam, the superheated steam. Guys, do not confuse each to another. That's why I was mentioning that on the steam, to say if it is not given, use the superheated steam table, because you might be tempted to use another specific heat capacity where it is not used. So the change in temperature, remember, these are the flue gases which are at the chimney, and we are given the best temperature of the chimney, which is 177,09 degrees Celsius, minus T in, the input, which is the input there of 25. So that's, we are using the best temperature of the chimney minus the input. That's the change in temperature, just like that. Just like that. So that we have got the Q for the what? We have got the Q for the in this case for the dry gases, which is going to be, from my calculation, I got something like 309.1,9. That will be 9999997. In this case, I'm not going to round it off, guys. I'm just going to take it like as it is, so that we have exactly answer. But yes, you can even round off. I'm not saying it's wrong to round off. I'm just going to use it as it is, guys. So if I take this, remember I said I need a percentage, so it can at least help me to have a better percentage here. So you're going to have our percentage as a Q for the gases, the flue gases here, which is 3091,9897 over the calorific value. Remember, this is kilojoules per kilogram, kilojoules per kilogram. So your calorific value also must have the same units, kilojoules per what? Per kilogram. And we have that. Remember, our calorific value, we said, is what? 32,000 here, 32,000. And the kilojoules, the units there, they are fine. So that's 32,000. It is in kilojoules per kilogram times 100%. So that was going to give us the percentage of this. So this is going to give us 9.66 to 2 decimal places. So that was the percentage of the what? Of the heat carried away with the flue gases at the chimney. And also they mentioned for you that at the chimney, you're supposed to know that the air is the one that is at the preheater, the air preheater. So at the chimney, we've got the flue gases. So if you understand this, guys, you can answer any question, especially understanding when you are given the specific heat capacities for each. We can calculate the heat that is absorbed at each point, the heat absorbed by anything, the heat that is taken by the flue gases, the heat at the preheater. We can talk of the heat at the, the one with the specific heat capacity. Then we talk about the heat at the evaporator. But when you talk about the evaporator, now we are back to the steam. We are talking about the water, the steam. We are using the enthalpies H4 minus H3. The one for the evaporator, H3 minus H2. The economizer, H2 minus H1. So the formulas, yes, all they represent heat absorbed. But this is from our diagram, this one. The air preheater is something else that is different. Something else that is different. So you must know your information. All right, so with this, guys, we shall have more questions that we need to focus on or talk about, because as you can see, yeah, we have a lot of things that we need to make a clarity so that you'll be able to answer any typical question that you are given. As long it's on a steam plant, you'll be able to answer it with the help of your steam table and the superheated steam table. That one, we need to have a question like that. We need a question like that, truly.